Hello, this is Mr. Craig, and I want to talk about nuclear chemistry. This is day 117 in the notes, and we're going to, in this video, I'll talk about some very basic nuclear type information here. So let's go ahead and get started here. First thing I want to point out is the difference between a nuclear reaction and a chemical reaction. Hopefully, we've had enough experience to where we recognize what a chemical reaction involves, and we probably haven't discussed too much about what nuclear reactions involve. But the one most important thing that we have to realize the difference between a nuclear reaction and a chemical reaction is, in a chemical reaction, the nucleus stays intact. We don't change anything about the nucleus itself. We're exchanging electrons when bonds are broken and when bonds are formed in chemical reactions. But in a nuclear reaction, the nucleus is not the same. In other words, protons are being converted into neutrons, neutrons can be converted into neutrons. Things are changing. So don't mistake or try to put a nuclear reaction and a chemical reaction in the same category, because there's two completely opposite things going on here. Also, when we talk about a nuclear reaction, there is a high amount of energy that's being released from this reaction. And we've all seen pictures of nuclear bombs going off. So there's a great deal of energy that's being exchanged when a nuclear reaction takes place, as opposed to a chemical reaction. All right, let's see. Radioactivity. Radioactivity is the spontaneous decay of particles from the nucleus of an atom. And we'll talk about what decay is here when we do some of the examples at the end of the problem. But we should be able to recognize, based on thermodynamics and with Gibbs free energy, what spontaneous actually deals with, what spontaneous actually means. So we shouldn't have to worry, oh, we have to do something to this reaction to get it going. Well, if it's radioactive, it's going to do it on its own. That is, by definition, a spontaneous reaction. The types of reactions. So we'll talk about the types of reactions, and I'll give an example of each one. There are 5 main types of emissions. There's alpha emission, beta emission, positron emission, electron capture, and gamma emission. We won't do a whole lot with the gamma emission. Just know that those are that's the worst scenario that can take place if we are around a nuclear reaction. We don't really want to be around one of those, which is kind of nice because those take place in deep space, near a black hole and with stars, so we're kind of safe here. So let's go ahead and get right into alpha emission. When we talk about emission, we're talking about something that is being ejected from the nucleus. Also, the term decay can be used. So when you hear emission, decay, I'm trying to think of another term if there is one, but what happens is that something is being ejected out of the nucleus. So when we talk about alpha emission, an alpha particle is nothing more than a helium atom with no electrons. So when we look at an atom and it has no electrons, we've actually made that atom a lot smaller. Now, helium with 2 electrons is already small by itself, but when we remove those extra electrons, we also have a positive charge on this thing. So even though we don't include the charge on the alpha particles, some people may do that, and it's okay if you don't. I think it's just understood that we don't have to worry about the charge being indicated on there. So typically when we talk about alpha particles, we're talking about a helium atom that has no electrons, and if it's alpha emission or alpha decay, it's being ejected from the nucleus. And what I want you to recognize on nuclear reactions, and we talked about this in general chem, nuclear reactions are probably the easiest ones to balance, because what we want to keep in check is the proton numbers, again, which are the numbers on the bottom. If you treat that arrow like like an equal sign, we want to make sure that we have the same number of protons on both sides. Also, when we deal with mass numbers, the numbers on top, we also want to make sure that we're treating that arrow like an equal sign. We want to have the same number of mass units on both sides of the arrow as well. So when we look at a balanced nuclear equation, these are, again, probably one of the easiest ones you can worry about, is that when I look at uranium, 238 here, and the 238 means the mass of the uranium. It has 92 protons, so when we eject a helium from the uranium, the thing that we have just created is now thorium, or this element TH here. So we have changed the makeup of the nucleus when something leaves the nucleus or when something enters the nucleus. So that's alpha emission. Beta emission, again, emission deals with ejection of something. A beta emission is nothing more than an electron. And there's actually two different types of electrons that exist. Now, in chemical reactions, electrons are always negative. We don't have to worry about any of the positively charged electrons. However, in nuclear reactions, there's what's called a positron, which is a positively charged electron. So we have to be aware of that, and I think I have an example of that here in the next one. But when we're talking about emission, again, it's something that's being ejected from the nucleus. And typically what happens is if an electron is ejected from the nucleus, we are converting a neutron into a proton. And again, we have to make sure that the numbers add up when we do this. So if you ever forget, who's being converted into what? Well, let the math tell you. So if we know that we start off with a neutron that has 0 protons here, and then again treating that arrow like an equal sign, an electron has a -1 value there because it doesn't have a proton. It actually has a -1 value. So that means it's changing neutrons into protons. So if I add up everything, I have -1 plus 1 gives me 0. So this is a very nice equation to help demonstrate that, yes, we are changing neutrons within the nucleus into protons. So if we change the proton, we're changing the element. We're changing something into more protons, we're changing the whole makeup of the element. Now, if we just change the number of neutrons, we're just changing the isotope. However, there will be a change in the nucleus. So here's another example where we have an electron that is ejected, and if we add up the values here, we should have 89 there. So again, we'll do some examples with that here in a moment. Positron emission, again, I kind of talked about it a little bit. It's a positively charged electron that is ejected from the nucleus. However, if a positron is ejected from the nucleus, we're not converting a neutron into a proton, but we're converting a proton into a neutron. So that's the mechanism that's taking place with a positron. And we can see an example of that where we have carbon-11 that has a positron that's ejected from it, and we now create boron. So we have changed a proton, which is in carbon, into a neutron, so we should expect the proton number to decrease. And it has. All right, on the back side, electron capture. Capture simply states that we are capturing something within the nucleus. So the nucleus is capturing that particle. Now again, this capture can deal with many particles. It doesn't have to be just one. But these are our most common. So again, if we are capturing an electron, what we're essentially doing is we're converting a proton into a neutron. Again, let the math tell you what's happening here. So proton again has a +1 charge. If I capture a negatively charged electron that has that -1 there, we have now successfully converted that proton into a neutron. And looking at gamma radiation, you won't be expected to have to know this for a test or for the AP exam. Just realize that if we have a positron and an electron come in contact with each other, we're forming two very nasty particles here, which are gamma particles. So I just want you to be exposed to that knowledge, but I don't really care if you remember past today, to be honest. All right, looking at some examples here. Predict a type of radiation. So when we do these types of problems, we need to have a periodic table nearby. So here I have thorium-230. It undergoes some type of decay to produce radium-88. So what we have to do is when we look at these equations, we have to realize, okay, again, the arrow is acting like an equal sign. So we have to make sure that the values on the bottom add up. So I have an 88 for the radium, So that to get it to 90, that means my particle needs to have a 2 on the bottom. Also, when I look at the mass numbers, I have a value of 226, where the thorium has a mass of 230. So that means that I need to have a mass of 4. So then I have to go back and figure out, okay, well, what are my particles that I have? So again, looking at your particles that you should be familiar with, actually let me make a list of those. You should know an alpha particle. You should know a electron. You should know a positron. You should know a neutron, which has a number of protons at 0 but has a mass of 1. And you also should know the proton, which can be identified as a hydrogen atom. I'm trying to remember, is that all of them? If not, I'll recall here in a second. Okay, so those are our particles that we need to know. So the 4 and the 2, obviously, that's an alpha particle. Okay. That one wasn't very difficult. Looking at the next example here, where we have bismuth and it captures an electron. So what that means is that A3 minus 1, means I have a proton number of 82, 209. Again, when we go to our periodic table, we don't care about the 209, we care about the 82. So when we go to our periodic table, find element number 82, and it looks like it's lead here. So the lead, okay, that looks like that's our element that we're going to be concerned about here. So let's put a PB on there. Oops. Good draw. Okay, so lead. So have your periodic table nearby here. Okay, and that one is just fine there. All right, uranium-238 ejects an alpha particle. So that means that we have 90 protons remaining. 238 minus 4 is 234. Again, we don't care about the mass number, but we do care about the proton number. So proton number 90. So 90 is thorium. This is going to be a pain in the rear here. So, okay, so TH. And notice that the thorium-234, the actual mass of thorium, 232.04. What I don't want you doing is getting hung up and go, wait a minute, those masses aren't the same that's on the periodic table. We don't care. Flat out, we do not care what the mass values are. We only care about the proton numbers. Okay, there's lots and lots of isotopes that exist. You're never going to be required to memorize them. Just realize that there are isotopes that exist. So you don't have to worry about the mass number that's on the periodic table. Again, remember that the mass number is the average of all the isotopes that exist in nature. So we don't have to worry about, well, which one is it? Well, in this case, it's thorium-234. All right, so let's look at the next example. Looks like we have an alpha particle that is, I'm sorry, not an alpha, but a positron particle that's ejected. You should be able to also verbalize these and say what's happening, not just be able to find what it is that we're looking for. Okay, so since we have an 84 over here and a 1, that means we have to have a proton number of 83, and the mass is still going to be 209. So we need to find our element that's 83, and it looks like it's up here. Looks like bismuth. Okay, so we want to go back, and let's get bismuth. So Bi. Okay, so bismuth 209 in that case. All right, and the last one for here, E, we have a proton number of 103 and 104, so that means that we have to, whoops, not a 0 there, sorry. It means we have a +1. And the mass is 0, so we have to go and, well, that's a positron. We don't have to go to the periodic table on that one. All right, so we know our particle is a positron in that one. All right, looking at the next couple here, the last 3, we have Einsteinium-252 undergoes alpha decay to form. So what we want to do is write this out. So we have, let's see, I think I have room here. Einsteinium 252. And we have to go, put the S on there. We have to go to the periodic table and find out what Einsteinium's, yes, 99. Okay, so go back, whoops. So 99 is his proton number, or its proton number. Undergoes alpha decay, that means arrow. And alpha decay is, alpha decay is 4,2 with a helium. And then, since we had alpha decay, we need to make sure that those numbers add up. So we have 97 protons, and our mass will be 248. So whatever element 97 is. And in this case, it is berkelium, BK. So we want to go do that. So BK. Okay. So you should be able to write out a sentence as well in doing something like this. All right. G, nitrogen 15. And again, the 15 is its mass number. Nitrogen's proton is 7, and you can check that on the periodic table if you like. Undergoes electron capture, so that means plus. So electrons have a mass of 0, and electrons negatively charged, so arrow. So 7 minus 1 is a 6. The mass remains the same. And element number 6 is good old carbon. Okay, lead 209. So Pb 209. And lead's number is 82. Just did that not too long ago. 82. It undergoes alpha decay, so arrow. Again, alpha is a 4, 2. So that means we have a mass of 205 and 80 protons. And so 80 protons is good old mercury. So Hg. Okay. And again, I don't think that doing these types of problems are extremely difficult. I would expect to see questions like this on the multiple choice portion of the AP exam. I highly doubt if you're going to see questions like this in the free response section. Stay tuned for the next video. I hope if you have any questions, don't hesitate to ask.